Welcome back. The main drawback of the continuous Fourier transform of a discrete signal is that it is not a computable transform. Unless the image has a closed form expression, its Fourier transform cannot be computed. Based on the material of the previous segment, we will show in this segment that a sampled version of one period of the continuous Fourier transform is all that is needed to represent a discrete image. This represents the discrete Fourier transform, or DFT, which maps m by n samples of an image in the spatial domain into m by n samples in the discrete frequency domain. In addition, what makes the DFT such a useful tool is that there are fast ways to compute it, collectively referred to as fast Fourier transforms, or FFTs. We will look at some examples of spectra of images in this segment using FFTs. So, let us proceed with this interesting and useful material. Let us see in more detail some of the parts we covered in the previous slide. Here again is the definition of the continuous Fourier transform of a discrete time signal x n1 and 2. It's an n1 by n2 signal. That's the support of the signal. This is a very useful transform, and we've spent quite some time talking about it because it allows us to describe, characterize, analyze images in the frequency domain. The main drawback of it, however, is that it is not a computable transform. I have to find x at all possible frequencies. Omega 1, omega 2 are continuous quantities. So if I have an analytic form for x n1 and 2, then it is possible to find a closed form expression for x omega 1, omega 2, as was the case with the simple examples we did in the previous slides. If, however, I want to find the continuous Fourier transform of an image that I acquired with my digital camera, then clearly I don't have an analytical expression for the image, and therefore I'm not able to find an analytical expression for x omega 1, omega 2. So what we saw in the previous slide is that I can sample the Fourier transform x omega 1, omega 2 at equally spaced frequencies, and the spacing between the frequencies is 2 pi over n1 in the horizontal direction and 2 pi over n2 in the vertical direction. And by doing this sampling of the frequency domain, I only keep one period. So k1 is from 0 to n1 minus 1, k2 between 0 and n2 minus 1, and again this is for an n1 by n2 image. So if I substitute 2 pi over n1 for omega 1 and 2 pi over n2 for omega 2 here, I end up with this expression, which is the forward discrete Fourier transform, DFT. It gives me a description of the image in the discrete frequency domain, k1, k2, where k1, k2 range over one period, as shown here. And this is clearly a computable transform because it only involves a finite summation, therefore a finite number of operations. The inverse Fourier transform shown here takes me from the frequency, the discrete frequency domain, back to the discrete spatial domain. Algorithmically has the same structure as the forward transform, the only difference being that here I have e to the plus j, the exponential, while here is e to the minus j, and I also have this normalization factor in the front. So this here is the discrete Fourier transform pair that maps n1 by n2 discrete space images, samples, to n1 by n2 samples of the Fourier domain, of the Fourier transform in the frequency domain. It's an exact transform. I can go back and forth between xk1, k2, and xn1 and 2 with no error. And it makes sense since an n1 by n2 image is mapped to another n1 by n2 image, both discrete, and therefore I don't need infinitely many frequencies to represent the signal in the frequency domain. Actually, even if the image is real, the DFT is complex, so it seems that I'm mapping n1 by n2 real numbers into n1 by n2 complex numbers. However, the property of the Fourier transform, that the Hermitian property that we studied, holds true here for the DFT. That is, when xn1 and 2 is real, the magnitude of xk1, k2 has even symmetry, while the phase has odd symmetry. Therefore, I'm mapping n1 by n2 real numbers into n1 by n2 over 4 complex numbers, and assuming that one complex number corresponds to 2 real numbers, I have the same number of numbers in both domains. The DFT and the Fourier transform share many, if not all, of their properties. One main difference, however, is that the linear shifts in the Fourier transform become, when it comes to DFT, circular shifts. One way to perform and understand circular shifts is to periodically extend the image and then perform a linear shift, but only keep the central part of the image, the baseband, or the image that is defined by n1 and 2 in this window here. By looking at the definition of the discrete Fourier transform, it is clear that it is a computable transform. It involves a finite number of computations. The same statement is true also for the inverse discrete Fourier transform. However, what made the DFT a very popular, you might say, transform is the fact that there exist computationally efficient algorithms to compute it, which collectively are referred to as fast Fourier transforms. So an FFT is not yet another transform, it's simply an efficient way to compute the DFT. So let's see how many multiplications we need if we directly compute the DFT. We see that for each frequency k1, k2, we need n1 and 2 complex multiplications due to the multiplication of the signal by these complex exponentials. Since I have n1 and 2 frequencies, I need n1 squared and 2 squared complex multiplications. Clearly, if n1 equals n2 equals n, then I need, in this case, n to the 4th complex multiplications. I can do better than that by reorganizing the terms in the definition of the DFT. So I see that what's inside the brackets is the one-dimensional DFT of the signal with respect to n2. So if here is my image, so n1 and 2 is the orientation of the axis, so x, n1 and 2, what the summation inside the brackets is doing is computing the one-dimensional DFT of the rows of the image. This signal then inside the brackets is, I'll call it G, is a function of n1 and k2. With this, I can then rewrite the DFT as shown here. And what this last expression tells me is that if I take G n1 k2 is a function of n1 and k2, according to this summation, I now perform the one-dimensional DFT of each of the columns of this signal. Hence the name row-column decomposition. First, we take one-dimensional DFTs of the rows, followed by one-dimensional DFTs of the columns. So let's see how many computations we need of this row-column decomposition if I directly compute the one-dimensional DFTs. So what we've done is to first take n1 and 2-point one-dimensional DFTs, and if again directly computed, I need n2 squared multiplications. And then we take n2 n1-point DFTs, and for that I need n1 squared multiplications. This is clearly equal to this. So again, for n1 equals n2 equals n, I see that I need 2 n to the 3rd multiplication. So by just exploiting this decomposability structure of the DFT, I see I can bring the number of multiplications down by an order of magnitude. I can do even better than that, since I have fast Fourier transforms to compute one-dimensional DFTs, and these transforms date back to the mid-60s, so 1965, Cooley and Taki were the first people to invent such fast Fourier transforms, and by and large their development gave a big push to the whole field of DSP, since now we were able to efficiently, maybe real time in some cases, implement algorithms that were very hard to implement before that. So using one of those FFTs, I can compute an n1 point one-dimensional DFT by using n2 over 2 log 2 n2 multiplications, and then for computing the n1 point DFTs I need n1 over 2 log n1, and this is clearly equal to n1 or n2 over 2 log n1 and 2. So we see here that for n1 equals n2 equals n, I need n squared log 2n multiplications. So we brought down the number of multiplications by another order of magnitude. And this is actually, in most cases, the way to implement the two-dimensional DFT, by following the row-column decomposition and then utilizing efficient algorithms to compute the one-dimensional DFT. I can do better than that if I use a so-called radix 2x2 FFT, and I bring down the computations to 3/4 n squared log 2n. Armed with the DFT, which is a computable transform, and even more specifically with an FFT, a fast way to implement it, I can see how an image looks in the frequency domain. So here is the orientation of the axis, n1, n2, and this is a 392 by 294 pixel image, and there are 8 bits per pixel. So here in the middle I see the DFT of this image. So it's a 392 by 294 point DFT. So here is the point 2 pi, I guess half of this 196 is the point pi, and about here 147 is the point pi. So here in the middle is the highest frequency, the pi frequency. So in the middle you see a mesh plot of the DFT, the magnitude of the DFT, while on the right you see an image version of it, and it's color coded. So red here is high values and blue are the lower cold values. So you can see that there's a lot of energy at low frequencies. This is the 0, 0. There's a peak there, and the magnitude of the DFT drops off as I approach higher frequencies. So here we see the same image again on the left, but often it's more informative if the magnitude of the spectrum of the image is centered. So in other words, the 0 point is around about here, and therefore here is minus pi, pi, and minus pi, pi in the other direction. So we see here more clearly that there is a peak at 0, 0, and then as I move away from that frequency, as the frequencies increase in all directions, the magnitude drops off, becomes much smaller. The question is, how can I center the spectrum as shown here? And one way to do it is by multiplying the image by -1 to the n1 plus n2. So this is a checkerboard pattern. It alternates between -1 and 1. And why would such a multiplication center the spectrum? because this is clearly to e to the minus j pi n1 plus n2. So in the spatial domain, I multiply my signal with this complex exponential, and one of the properties of the DFT is that this introduces a circular shift of the DFT by pi pi. We saw this property actually, I believe, when we talked about the Fourier transform, and there the complex exponential in the spatial domain gave rise to a linear shift, but here it's a circular shift. So circular shift, one of the ways again to look at it is that I take the spectrum, I periodically extend it, I shift it linearly by pi pi in both directions, but then I only maintain the base period, the one shown here, right, from 0 to 392 and 0 to 294. And again here you see the spectrum as an image, so the high value is at 0, 0 centered, and again this provides in most cases a better visualization of the spectrum.